Good evening and welcome to this evening's webinar, IB with TI-Nspire Functions and Algebra. My name's Rodney Anderson. I'll be your host for the webinar. This webinar is being recorded, will be available to view at a later date, but you'll also be able to download documents on a link that will be sent to you over the next few days the panelists demonstrate. It is recommended that you view the webinar and not try the activities, as you can watch live and you can pause, fast forward and rewind the recorded webinars at a later date. If you have any questions, move your cursor to the top of the screen and open up a drop-down icon. If you have any questions, click on the chat icon there and direct it to me, the host. Now, you can also listen to the webinar via your computer. You can also listen to it via your phone. And you'll see that the meeting number tonight is 824-631-045. Dial in with that toll-free number and follow the instructions and you'll be able to listen via your phone. Feedback. It's always important to give feedback to the presenters and TInspire Australia. So at the end of this webinar, in conclusion, you'll find there is a survey to complete. It won't take too long. It's great to give feedback to the presenters and TInspire Australia and to improve their services. In a day or two, you'll actually receive an email that contains a link to your webinar certificate, which is great for your professional development portfolio, and links to download the documents. One of the panellists tonight is Bojana Graham, very, very experienced from Wesley College. Hello, Bojana. She's there.
Hello, everyone.
There we are, Bojana. And a colleague from her college as well is starting tonight is Pam Durrant. And Pam is very experienced as well, so welcome, Pam.
Hello, everyone.
So, Pam, you'll be starting shortly, so you'll be able to share your screen, so we're ready to go. There you go, Pam, the ball's in your court now. You can start the first point of the game.
Okay, well, hello, everyone. I think we're all systems go.
Yep, see your screen.
So, yes, it's shared. Can everyone see my screen? Good.
That's correct.
Okay, so we're looking at functions and algebra for the IB program, so it's the non-cas calculator, and I thought I'd start off firstly looking at some composite functions, as these come up quite a lot in standard level and high level, and you can expect that they will be on the exams. So we're looking at FOG or GOF, or f of g of x, g of f of x. So what I wanted to look is perhaps a little activity you could do with your class to get them started on thinking about why the domains are what they are, and what does it look like when you put one function inside another. So I've got here two functions, f1 of x being x minus 3 and f2 of x being x squared. So these are just beginner functions, probably aimed more at standard level, but certainly you could use it in high level. So I'm going to get the function entry bar up, and you can do that in a couple of ways, through the menu icon, but I like to use Control G. And so what I'm going to do is type in the composite function, f1 of f2 of x. So I could actually type in the function x squared minus 3, but it's really nice to look at the functionality of the computer and the calculator and what it's able to do. So I do this now and I hit enter, and up comes my composite function. And you can see immediately that yes, it's obviously parabolic, but interestingly, the turning point is now exactly where the y-intercept is of f1 of x. So I'm also going to put in the other way, so f2, and you'll notice that when it comes in f2 up here, it's in bold, and that's because f2 is already defined by me entering that first function. So f2 of f1, and we can see the comparison there of those two graphs. And what we can see is, while I said that the first one, x squared minus 3, has its vertex at the y-intercept of x minus 3, the x minus 3 all squared has its vertex at the x-intercept of the straight line. So it's quite nice to then go into a discussion with your class about why that is. What are the values that we're putting into the function, and then what are the overall values that are coming out. So we can have a look at a few values using the trace function and the graph trace. And you'll notice it's got this little icon here. Once you're in graph trace, you actually have to escape to get out of that. And immediately, graph trace will go to the very first function you've got defined on that page, and it'll generally try to find the y-intercept, so let x be 0. So having got that, I can then use the up arrows of the keypad and go to the other functions at that same x value, so the f2 function, then the f3 function, and then the f4 function, and going back down through those. But I can also move across, so if I move across with the right arrow, and I can get to the other 0, and once again I now see that the input value is 3 in there, but I can have a look at what happens when I go to the other values that correspond to that same x value. Okay, so moving along to 2 new functions, so making it a little bit more exciting, because there's always more excitement if there is a break in the domain to begin with. So I've got 2 functions here, one on x and x squared minus 4. So I'll just quickly enter the f of g of x, g of f of x. So in this case it's f5 of f6 of x. Okay. And straight away we can see that this one, putting the x squared minus 4 into the reciprocal graph, we get a really interesting shape. And what we can see is that there are 2 the original f5 of x. And why does that happen? So what we can see is that it looks like those breaks in the graph, F7 here, are lining up with those x-intercepts of the parabola. Well, let's have a look at that, because those x-intercepts we can find. So using the menu trace, graph trace, I can find, well, I can see it's x squared minus 4, so I'm going to put in x being 2 and negative 2. So I can actually just type the value 2, and up comes the little x equals here, and I press enter, and it tells me that on F5, that's the 0.2.5, that's not that exciting. On F6, that's the 0, and on F7, it actually draws in an asymptote, a dotted line to say it's undefined. So we can see quite clearly that one of the asymptotes of that composite arrangement is at x equals 2. And while we're still in graph trace, I can now just put in negative 2, and notice that the little pop-up comes back, and I can go there, and because I was last on F7, it stayed there, and it's telling me, hello, there's another asymptote happening there. And we can see if we just go down, oops, if I actually go back to negative 2 now, that's another x-intercept of the parabola. So we can have a look at why the intercepts happen at the x-intercept. So we're putting in a value that gives us that function being 0, and if we put that into the denominator of 1 on x, then naturally we get the undefined. But it's interesting that, you know, those 2 originally fairly simple graphs combine to give that third graph, which is more complicated. So let's have a look at F6 of F5 of x. And I'll just move those labels out of the way. There we are. And once again, what we can see here is that, well, it's obviously asymptotic, and it's asymptotic where we had the asymptote before, but now it's actually shifted down, and it looks like there seems to be a horizontal asymptote which is lining up quite closely with that y-intercept. So there's a lot of discussions that you can have with your students about where all of that is happening. Okay, so 2 new graphs. This is probably more into high level now, or quite advanced standard level type things using the log function and a parabola. But these produce some nice composite functions. So if I do f9 of f10 of x, and what we can see there is that this graph actually has a big gap there where there is no function defined. And we can have a look at that. Once again, we can see that the parabola, its x-intercepts, are dictating where the vertical asymptotes are of the composite function. So the menu trace, once again, is always good. Graph trace. This time, the intercept being the function x squared minus 2 will be at the square root of 2. Now, when you're wanting to type in, can't actually access the square root button, but I can type SQRT, and you notice that if I just go back to SQR, it's going, well, that's just a combination of letters, but adding the T in, it goes, oh, you want to use the square root. So if I put a bracket now and put 2, enter, there is that function, F9, but the F10 is the interesting one because that is the 0, and of course the F11 gives us that undefined, and we can see the asymptote happening. But while I'm there, let's just have a look at what's happening at 0, and it tells me again it's undefined. Now this isn't the asymptote, even though they've drawn it as an asymptote for F11, it's actually just there is no function defined in that area. So if I go to -1, the same thing, but if I want to go to negative the square root of 2, I can see that that's just about the end of it, and in fact, of course, it is, because it looks like we're at that start of the graph there. So I'll escape from graph trace, Control G, and put in F10 of F9 of X. And here's a really interesting graph. Well, of course, all the graphs are interesting, but here's a really interesting graph, and we can see once again we've got that vertical asymptote, and it's lining up with where that y-intercept is happening there, but we're getting this shape which almost looks linear at this point here, but is it? So, you know, there's something that you can also discuss with your students as to what's happening, why is that combination giving us this graph where we get that turning point, and we can see the parabola had a turning point, so that follows, but why is it stretching out like this? So we can talk about how steep the parabola is expanding and the log graph, how that is going, and then the effect that one inside the other has overall. And you could just give the kids a bit of a task. Can you actually fit a straight line to that, a bit like the old green globs type thing, trying to fit lines to various shapes that they've got? And in fact, once you try and put a straight line on that, you'll find that it is in fact not linear at all. But it's a nice little challenge for them. Okay, lastly, for the high level kids, using the log base E and the sine X graphs, these produce some really nice graphs and really illustrate the whole domain part. So this is F13 of F14 of X. And I don't actually have to type in those brackets because the TInspire is so clever. It knows that I'm going to want those brackets closed, so I can just press enter at that point. And we see these lovely graphs here where we have lots that is undefined in between, and then these lovely little graphs here where we've got that whole function that looks a bit like sec or cosec, but with lots of gaps in between. So talking about why that is. So it lines up, and if you have a look, we can do a quick graph trace. At 0 is good. And if I just get onto the blue graph, there we can see that it's undefined, and we can have a look and say, well, that's obviously an asymptote for this graph here, and then we don't have another one until we have our x-intercept of the sine graph again, and that's of course because we're putting the sine graph into the log graph, and log is not defined for any negative or 0 values. So we don't get anything in our domain here of our composite function when we don't have values that can fit in. So it's coming back to what is going to make a function that we can use. So what domain would be possible. And lastly, just having a look at the other way around, f14 of f13 of x. And once again, a really unusual graph comes out of that. We can see it's got a turning point here, and then we've got it following the log graph, and then it trying to come back down. And if we zoom out, we could have a good look at what happens later on. But, you know, some fascinating graph shapes are possible using our composite functions if we don't just restrict ourselves to the regular ones that we see in exams. One of the activities I really like to do is to have a whole lot of functions, and I draw them out of a hat and I give them to my students in pairs, 2 functions at a time, and they then use their calculators to explore every possible combination they can do with those 2 graphs. One of which part is doing the composite log and goth, but of course doing reciprocal, sum, products, different graphs, etc. So it's a really fun activity in getting them to display that on poster paper later. Okay, my next part of the presentation I wanted to talk about how we can do different ways to solve using the features of the calculator. So there are some ways that are more efficient than others, and you know, it just depends on what the type of question is asking. But places where students can access the ability to solve, there are 3 directly on the Calculate page. I like to also use the Listen spreadsheet, and of course we can use the graph page. And the graphical approach by far is used much more in IB exams than any of the others, but that's why I just wanted to highlight the others as well. So there are the 3 ways on the calculator page, the nsolve, the linsolve and the polyroots. So let's get started with some of those. So nsolve is a numerical solving feature. It only gives answers, and it will only give one answer at a time, and it will try to give the answer that is closest to 0 and is positive. It's located in the menu, algebra button there, and we're going to use it to solve a couple of equations. So let's get started. I'll show you where that is. So menu, algebra, and you can see there are 3 solving tools. So we're looking at numerical solve, and it comes up with nsolve. If you're particularly skilled with the keypad, you can just type in nsolve and open a bracket. So I'm going to put in e to the x minus 1, oops, there we go, always got to go to the side there, minus 1/2 is equal to 4 sine x. Now notice I just typed in sine, but I could get it from the trig menu. And I want to solve that for x between 0 and 2 pi. So at this stage I'm just going to say solve that for x, and it tells me there is an answer of 0.173. So that's my first answer. I then can go up and up again and grab that. And if I hit it again, I'll just get the same answer. So I need to tell it to move on. So I'm going to use the given symbol, which is located on the equals menu. So x is greater than 0.17. And if I actually put in 173, that's not big enough and it'll give me the same answer again. So I'm going to go 174.
Did you want greater than or less than?
Oh, sorry. Thank you. Greater than. Greater than. There we are. And it tells me there's another answer at 1.5. Is that it? Do I need any more? So I can just edit that, and that's the wonderful thing about these calculators. So if I put in 1.51, it tells me that there are no solutions left to find. So there were only the two solutions between 0 and 2 pi at 0.173 and at 1.501. Okay, so let's try another one. So menu 3.1. If we have e to the x, the x there equals 5 minus 2x squared. Now, in this case, I'll just flick back to my question page. I want to find a solution that is greater than 1. So there are a couple of solutions to this. So if I have a specific target that I want to be near and it's going to be greater than, then I can actually just tell it, start at 1 and start looking there. So this is a nice little feature. So if you know there is a solution that is between 2 and 3, which some exam questions have, you can actually just say start at 2. And there it tells me the answer is 1.04. So it's like giving it a clue as to where to start. Okay, the next feature is linsolve, and this is really good for solving a system of linear equations. It's also located in the menu algebra. And so I'm going to use it today to look at the higher level question of an intersection of 3 planes. So I'll move across. So menu algebra, and it's the system of linear equations. It drops down a template here. I need 3 equations, and as soon as I tab out of that, it immediately puts in the extra variable that I need. It then sets it up in the bracketed way with x, y, z. You could type in linsolve and you could get to that same thing through the little favourites menu there and set that up yourself, but it's much easier to do it through linsolve. So we've got x plus 2y plus z equals 0. If I press tab, it takes me to the next line entry, so 2x plus y minus z, oops, that's z, equals negative 6. And tab into the third one, 3x minus y plus 4z equals negative 6. So my 3 equations, and it tells me that my x, y and z are negative 3, 1, 1. So that's my point of intersection. But what happens if there isn't a point of intersection? So I'm just going to change this one back here, there, to a negative, and what we find is that there is no solution to be found. So this is saying that those 3 planes do not intersect at a point or a line. Okay, what about if I just delete equation 3 altogether? So if I just go backspace to there and enter, what we get is the beautiful parametric form. So the TInspire will always, because our 2 planes will meet at a line, the TInspire will always give us a parameter in the z variable, and then it will list the x and y in terms of that parameter. So their parameters are always C1, C2, C3, etc., counting through as we stay in the same problem. So this is saying if z equals t, then y is 2 minus t, and x is t minus 4. All right, so one last one for that. Algebra there. I'll go through equations again. And this time I'm going to put in 2x plus 3y plus z equals -5. X plus 2y minus 2z equals -9. And 3x plus 4y plus 4z equals -1. Hitting enter, and what we can see is these three planes meet in a line where once again z is equal to the parameter t, if you like, then y is 5t minus 13 and x is 17 minus 8t. And as I said, generally the parameter will always be given as the z, or if it's only in 2 dimensions, then it would be in the y. Okay, the next way that you can solve is with the polyroots and the C polyroots. So for those of you shifting from the TI-84, you will have known these two programs, the LinSolve and the polyroots, as part of the PolySimult app. So this is the version in TInspire. So once again, menu algebra. So we can do quadratics over R and over C, and the cubics the same. So over R, it's just polyroots, and over C, it's C polyroots. So that makes that nice and easy. So menu algebra, polynomial tools, and I'll do a quadratic first of all with real roots. And it has this beautiful drop-down menu, just like in the old PolySimult. And I'm going to put in 3, -1, and -2. And I press enter, and up come my two possible solutions. If I change that -2 to +2, we can see an empty bracket, which means there are no solutions to that. Well, in actual fact, no real solutions. So if I grab that again and I just put a C at the front and press enter, it in fact tells me that there are two complex solutions, 1/6 minus essentially 0.8i and 1/6 plus 0.8i, and you can see that if you scroll across. Right, so doing that in 3 degrees there, we can go straight to the complex. And so if I go in with 1, -3, -1, and -2, and I press enter, here are my three solutions. So -0.2, 28, minus 0.7i, -0.228 plus 0.725i, and then 3.457 as our real solution there. The other thing I can do with that, I just go up and grab those and enter, and go to the very start of those solutions. If I now just type sum, oops, missing a bracket, it will tell me that the sum of those solutions is 3, which is really nice to bring in that whole conjugate root theorem. Okay. We're almost out of time. I'll just quickly go through some regression. So regression can be another useful feature when you have a particular function shown and the the students need to generate the values of the coefficients. So there are many regressions in the statistics menu that you can do. So we need to open up a list and spreadsheet page, and I'll just show you the graph that we're going to model. And what we can see is there are 3 known points, plus we're shown that it goes through the origin. And it is a cubic equation, so we need those 4 points. So if we go to a spreadsheet, I can put in those coordinates, so -2, all over the place there, 0, 1 and 2 with my x values, and if I go up and put in the matching y values, 0, 2 and 0. Now, it makes life easier with the spreadsheets if you actually name your list. So I'm going to call these the X's and these the Y's. I don't use X and Y because they're already defined within the TI-Nspire, and it causes a bit of a problem. So if you can call them something other than X and Y, that's very helpful. So menu statistics, oops, let me just go back there. In stat calculation, sorry, that was all too quick, I'll just escape that. Menu, statistics number 4, number 1, stat calculations, and we're going to cubic regression, but you can see there are many regressions there that you can choose, and it keeps going. So I've put the X values in as the X's. I then go to the next one, the Y's, and if I just tab down, telling me it's going to put the next values into the next column, and so I can press that, and what I can see is the coefficients of the A, the B, the C, and the D. The D is really interesting because essentially you would call that 0, certainly to 3 significant figures, and of course because it had that 0, 0, it was going to be x-intercept of 0. So that's another way that the students can actually find a function rather than solving simultaneous equations. Now I'm going to stop there. There is a little bit on graph solve, but you can see that in my post document that will be available after the webinar.
Well, thank you, Pam. You've covered a great deal in the first half hour of the webinar, and Virginia will be starting very shortly. And you've covered a great deal of the menu icons. And I hope the participants have taken notes and really enjoyed what you've done so far.
Pam and Rodney, getting to see my screen. Are we on?
Just about there, so
Okay.
waiting to come through. Yeah, we can see your screen, Bojana. Away you go.
Okay. So what I will start with is following what Pam was doing, and in operating system 4.2 is something new which is called pop-up menus in the calculator screen, and I will demonstrate how that works. So if I type x squared minus 4, and then I go to control menu, you see, and that is on the calculator, and I checked it actually works in press to test. I get the pop-up menu, and the calculator is guessing what I want to do. So I might want find root of a polynomial, so I'm saying yes, that's what I want, and it comes up with the table. Yes, I want the real roots here, and if I press enter, actually I don't need to go through menus, but I get the roots straight away. If I instead enter x squared plus, let's say, 16, and again I go control menu, and I want the roots as well, but this time I'm saying I want the complex roots, and if I press enter, it gives me the complex roots. So that is a nice shortcut and doesn't require the students to remember where things are, especially for study students. It might be quite handy. If I type x cubed minus 3 equals sine x, and then I go control menu. Now this time the calculator is guessing that I wish to solve. So yes, I do wish to solve, and interestingly it comes with this box. So again, it gives you the option to say, okay, my guess it might be 1, and again, if I know what domain I want to solve over, 1 to 5, I can put some guesses, and then it gives me the particular solution. So that's a new feature, and it is quite handy. The other thing we can do, we can say, let's say if I go x squared minus y squared equals 4, and this time I'm again saying control menu, and it comes up with this pop-up menu, and this time it's saying you probably want to graph it. So I'm saying yes, I do want to graph it, and it opens in the side window, and you can also see on the left-hand side everything which we had in the calculator screen, and you can switch between the windows and you can sketch any relationship in this way. So it's a new feature, and when I showed it to my students, they really loved it because, of course, you don't need to memorize where the things are, especially with C polyroots and real roots and domains domains over which we solve and so on. Now the students immediately ask, how do I get rid of the graph? So the easiest way is just press Control Z twice and the graph disappears. So that's one of the way we can get rid of the graph. Now following from here, and also what Pam was showing with the sum and the product, we can, in high level, of course, the students need to know what is the sum and the product of the roots of any polynomial, and this formula is not given in the formula booklet. So again, there is some nice investigation the students can do, sum and product of the roots of the polynomial. So there are some other features on the polynomial and so on. You can evaluate polynomial in a point, but you can find sum and product of the roots. So I written that in the notes page so I can illustrate. So for this quadratic, the sum of the roots is 3 and the product of the roots is 5. And then if I define here a quartic polynomial, and then I want to find the roots, I could do it this way, and from here I can find the sum and the product of the roots, and then look up how those two numbers are connected to the polynomial. That's one of the ways students can just check in the exam if they've forgotten that the sum of the roots is minus an on minus n minus 1 over n. So this coefficient minus this coefficient over that, and the product is the last coefficient over 1 on 4. So that's a nice investigation to introduce sum and product, and quite useful in the exam if they've forgotten the formula, and as I say, it's not written, unfortunately. So the other thing you can do here, you can actually, when you do it in class, you can use the random polynomial, and you say what degree you want, and then you can generate lots of different polynomials and then find the sum and product. With sum it works fine. With sum the product gives you this other bit which actually is 0, but so then it's probably good to choose sum which work properly. So again, that's one way of doing that. The other way, you can find the polyroots as we did, and then use sum and product by going up and down and so on. So that is another investigation. And then once the students did some investigation on sum and product of the roots, you can send them one of the questions via the navigator. If the polynomial is this quartic, then the sum of the root is, and they need to show actually what needs to be done, and then the product of the roots is, product should be here, of the roots is, and they need to show the steps, so not just using the calculator, but how they actually arrived at a particular solution here. So just a few ideas how that can be used, and that of course would be more for the high-level class. So I will close this document, and then we'll have a look at inverse relations and inverse functions. So what can be done now? We have, if I get a new graph screen, and I will start with the graph of x squared plus 2, and I sketch it, and now I want to draw an inverse graph. So if we go to menu graph entry, I can change it now to the relation. And remembering that that was my F1 graph, because that was the first new document, I can now say x equals F1, and it's bold because we already know what it is. And, sorry, I must have done something wrong. In y, of course, not in x, because we want the inverse. So x is F1 in y, so we swap x and y values, and we see what happens here. Additionally, we can draw our line. We need to go back to graph entry as the function x, and that's a nice discussion talking about if I have the quadratic and I find the inverse relation, is it the function? And clearly not, and that's how they can see what happens using the relations new feature in 4.2. However, that can only be used in class. Unfortunately, it is not going to work in press to test. So then we can start and check some other functions. So I have F3 graph here, and then I use again the relation x is F3 in y to actually create the inverse. So that's my F cube graph and the inverse graph, and this time clearly it's a function because for any x value there is only one y value. We could take it a bit further, and we can additionally add some sliders. So if I have e to a x plus b, so that's my graph, and then of course I might change the values of a and c, what is happening, and I can also change the values of b and watch what is happening on the graph. So that's quite interesting investigation, and in geometry, using geometry feature or even intersection works to give you the intersections here. So that is something which students can explore. The other thing, when we look at inverse functions, how can we restrict the domain of f in x to have an inverse function even though f in x is not 1 to 1? So again, you might have some slider here, and I have x minus 1 squared plus 2, and then when a is 0 or negative, clearly my inverse function, which is x in f1, is a function, but now if I go to 2, now the inverse is not a function. So that's a nice demonstration why it will not happen if we took like x values less than a has to be what the turning point is to get this reflection being the function. You can take it also further, looking at trying to form arcsine and arccos, just like saying why do we restrict the domain of sine in this particular way, and if I extend those things, clearly the inverse will not be a function, and that's how they can also look at inverse sine here, and similar thing with inverse cos, how those values can be changed and what is the maximal domain which can be used. And also we can play with varying the period of cos and seeing what happens and how it affects your domain and range here. So that is a nice activity looking at some inverse functions. Now, all those files, of course, are there. The next one, I might start with showing the Word document. So what we'll try to achieve here, we'll start with the function f in x, which is square root 9 minus x squared. And then we want to apply transformations to this square root graph. So we have vertical dilation, horizontal dilation, moving it up, down, right, left, and reflecting the x and y axis. And this time we would ask the students to say how many different designs, pictures can you create, and these are some of the ideas, how to get a rainbow, an eye, how can you model the McDonald's, and they are only allowed to use this particular function by changing it slightly. And so if we go to rainbow step by step, we can define this function. The reason defining it is good because then I can have all the other functions in terms of f in x, so they can see what happens. So the starting point will be to get all of them, and of course to change the color. If you press right click, you can go to line color and just take the colors of the rainbow in order. But this rainbow doesn't look like a rainbow quite yet. So what's done here, you can also go to attributes, and actually you can make the lines thicker. So that's how you can go left and right. So if I go left, it's just your basic line, but then I want those lines thickened. Notice I also changed the graph scale slightly just to fit the whole screen in one, the whole rainbow in one screen. But it's not, doesn't look very much like rainbow here. So now the task for the students will be how they can dilate those graphs to actually to get to something like that. And I have hidden the thing, but if you go and up, so the orange one, which is the one here, we use the dilation here, so we made it wider, and of course it's moved up. Then if I look at the yellow one, so compare the dilation between the orange and green, and then the red one, so there is something between those numbers in front of x, and that is quite a nice activity for them to see what's happening, and starting with f1 or f in x as defined. Now this one is an eye, which again we try to use the same function. So this time I started with using 0.8 square root 9 minus x squared and the particular axis. And then I reflect it, so I have the top part of the eye and then the bottom part of the eye. And then to create the middle, I used f1 in 3x and the reflection. And of course, if you want to shade in between, you could use analyze graph and the bounded area, and that will shade what you want and get the color in between. So there are some ideas about the transformations which would motivate students to create some pictures. And the other one is the McDonald's one, so I just took the picture and tried to get those lines as close as possible. And then if we leave it and change the axis, so I did just a very rough job here, but that gives you a general idea what can be done with just one graph and trying to change it. So Pam was talking about using regression. So I have a nice activity here for circular functions, and this is modeling monthly temperatures in Melbourne. And it happened in my class yesterday. I was actually doing this activity, and I said, so today we see whether we can model the Melbourne temperatures, and that was this wild weather yesterday, and the kids said, no, we can't, because it's unpredictable. but that was just a joke. So I said, okay, let's have a look at some actual average maximum minimum temperatures in Melbourne and what we can do with it. So just one explanation, then instead of graphing those temperatures against months like 1 to up to 12, it is done on a daily basis just to make it a bit more interesting, and it explains here how we can get those numbers that we are centering it on the average mean number of each month, and that explains what it is, but those numbers are given. So if I go back to this activity, oops, wrong one, temperature. So I need to go back to the start. So we have spreadsheet here, so I call that day and then T max and T minimum. So the students need to enter those temperatures from the handout. And then once it's entered, we need to go to purple graph, and then I want to have day on the horizontal axis and maximum temperature on the vertical axis. So does it look like a circular function? Yeah, a bit, students say. So let's try to see if we can fit the regression, and this time we want sinusoidal regression. I have changed, actually, if you go to menu and settings, you have this option display, and you can change them. Auto was, I think, 3 in this case, but you can change the settings not to have too many showing there and so on. So it's a nice discussion. So what does 6.67 tell us about? What is 19.5, and how can we get the period of this function? So that's one way of creating those graphs. The other way is getting them either in a spreadsheet or in the calculator screen. I like it in a calculator because we can go back and see a few things straight away there. So start calculations, and we go to sinusoidal regression, and we want day, and we want maximum temperature. Now it will save the regression line, which is also quite good. So I will have it saved in S3 because I already done it once. So it's a good idea because you see what A, B, C, and D are here. Now if I want to find the period of the graph, I would say the period should be 2 pi over, and what is it over? If I look at the graph, my n here on the calculator is this. I want this number. I could, of course, type it, but if I go to start, I can see that start B appears there, and it gives me the period 365 days. So that is something we can do, and if I repeat that for the other regression, so that's my max, and if I repeat it for the other regression, then in the graph screen, I can bring those two graphs together and say this is my maximum minimum temperature, and interesting comparisons that, of course, the period stays the same. Well, these are, we see that the peak is not at 0 or something. It will always give the sign regression, even if that's a cost function, because it will be translated pi onto right or left, and they can check the average temperature, maximum, minimum, that those were the average temperatures given on the handout as well. And of course they can use solve and so on. So if I now put the calculator screen, and one of those functions was, let's say, F3 in X, and I want it to be equal 21 degrees, and now if I go again, math actions, and I want to solve numerically, so I don't need to put the guess, but I might want to get the solutions between 0 and 365, and they say okay and enter. So it tells me on this day the temperature was 21 and so on. Only gives one value, but in this one cycle we would only see one value. If we want more cycles, then we could get some more values. So that is something we can do, modeling some sine graphs. Quickly, we're getting a bit out of time. Absolute value investigation, again, mainly for high level. So you can have a series of graphs, sketching F1 and the modulus of that, and this is some of the functions to investigate for students. So this is our function, and that's the modulus of this function, and once they go through some pairs of graphs, they will be asked to actually come up with the conclusion what happens to the graph of f in x when we want to sketch the graph of modulus f in x. And then the other bit is starting with f in x, what happens if we sketch f in modulus x, and that is a bit harder. So if my function is the blue line 2x minus 3, this is f1 in modulus x. And if they look at a couple of those, we start with the hyperbolic graph, and then this is the modulus graph. So touching the graph, they can actually see in color what happens. So now in color it works really well. And then you can go to the harder one, what happens if I have 2x minus 1 and I want the modulus in modulus, and how we can actually arrive at some conclusions here. So that's what I had to present, and all those files and worksheets you can find, you will be sent a link to in a few days. So back to you, Rodney.
Thank you, Bojana. Thank you, Pam. Both of you have demonstrated many features of the Inspire that we could use in our classrooms. I know personally that a few things that I've forgotten and I would probably need to review, and then what I'd like to do now is remind people that where do we go to look for our videos that have been recorded. So if you actually look at the Texas Instruments Australia website, if you're not sure, just education.ti.com/, and if you just type Australia, that's the website that comes up, and you'll see on the screen you've got many resources. For example, any of the files you might want to go into the Australian Curriculum Inspired, the junior, and then you've got the senior, select your relevant subjects. There's lots there. Obviously the webinars that have been recorded, here we go, we click into here and see how fast the internet was going okay tonight. And then you've seen this webinar tonight and what's coming up. So in a few weeks' time we've got Haley and Frank doing the VC methods implementation. So there's many webinars coming up, but you want to see the recorded webinars, so we click on the demand tab, and there we go there. So for example, on the 2nd of May we had Brian and Sanjeev, which was not long ago, as I said. Only you can actually play the webinar, we can actually download it, save it to external hard drive, and see the files that have been shared. So don't forget, when the webinar is concluded, you'll actually please complete this survey, and it'll give you feedback to the presenters and Texas Instruments Australia. And don't forget, look at your emails, and you'll see an email sent to you with a link to your certificate for participation and links to the files. So thank you, Bojana.
Thank you.
And thank you, Pam.
It was a pleasure.
Good evening, and we hope to see your participation in future webinars. Bye for now.